That'll teach you. I will begin with a word of prayer. Dear Father, we thank you for this day. I thank you for students. Just ask you, guide our work today, Lord. In your name I pray. Amen. All right. I need to remind myself our problem, because it's hard to solve a problem unless you have a problem to solve. But we are solving Laplace's equation today, among other things. And so the method for solving Laplace's equation, and so for us, that looks like uxx plus uyy equals to 0. And we're going to solve, what happened? Oh, okay. Come on. And so we're going to solve this Laplace equation by pretty much the same technique we've used in the last two kind of problems, the heat equation and the wave equation. So I'm going to solve this on the on a rectangle of sorts. Let's see if I drew it right. Yeah. So 0 less than or equal to x less than or equal to pi, 0 less than or equal to y less than or equal to 1. I want to solve Laplace's equation on this rectangle given certain boundary conditions. In particular, I want partial u partial x to be 0. So yeah, I want partial u partial x to be 0 at x equals to 0 and x equal to pi for each y, all right? And I'm also going to suppose that I want u of x 0 to be some given, say, let's say f of x. And I want u of x comma 1 just to be equal to 0. All right? Now, and this, I'm actually going to choose a specific thing. I'm going to say that this is equal to 4 times the cosine of 6x plus the cosine of 7x. We'll work through this one. But I want to put an f of x there to emphasize that we could do this for other functions, right? Like the way we're going to solve this, it's, you know, we could solve many similar problems if you understand what we're doing. And so let's see here, just to give you an interpretation, remember, we could think of an interpretation I'm fond of is electrostatics, all right? So one interpretation for this would be, you know, the electric field is minus the gradient of the voltage, right? So if I use U for the voltage, then the divergence of the electric field is minus noblis squared U. Well, that's minus uxx plus uyy if we're in 2 dimensions. So, and this would be equal to the charge density divided by epsilon naught. That rather suspect, here, if you'll allow me this rather unconventional written equality. This right here is Gauss's law in differential form. So in other words, uxx plus uyy equals to minus rho over epsilon naught. This guy right here, this is the so-called Poisson equation. All right. So what happens, so rho is the charge density. What happens when the charge density is 0? If the charge density is 0, then Poisson's equation just reduces to Laplace's equation, right? So a physical interpretation for the problem we're solving would be, we're trying to find the voltage function on this rectangle here, all right? And we have rho equals to 0 in here. And then we have these boundary conditions given, right? So like partial u partial x being 0, what would the significance of that be? In this interpretation, partial u partial x would be, minus the electric field component in the x direction. See, because the gradient of u is minus ux minus uy, right? So like partial u partial x would be negative the x component of the electric field. And so that boundary condition says the electric field is 0 on the x equals to 0 and x equals to pi edge. All right, that's what these boundary conditions say. Well, they don't say, they say that the x component to the electric field is 0 here and here, yeah? And the other boundary conditions, u of x 0 being f of x, so this right here, we're fixing voltage u equals to f of x, right? And then the other boundary condition is saying that the voltage is set to be 0 at the top edge. So you could arrange this setup through a particular, experimental setup. You could arrange these conditions, right? All right. Anyway, so that's the setup, and that's the one physical significance again here is that we're finding voltage as a function of position in the absence of charge. This is Laplace's equation. Okay, so how are we going to solve this? Well, separate variables. So we'll let u of x comma y equal to x of x times y of y. Yeah? Just like we did before, except with, time and space or whatever. And so then with this notation, uxx is x prime prime y, and uyy is x y prime prime, right? So uxx plus uyy equals to x prime prime y plus x y prime prime. That's all equal to 0. Hence what? Hence x prime prime divided by x is equal to minus y prime prime divided by y. Any questions? I mean, do you recognize the steps? You should have a strong sense of déjà vu. We did the same thing to start the solution to the heat equation and also to start the solution to the wave equation, right? Right? No? Still shell-shocked from the test? It's been like a whole week. Surely you've had turkey and so forth, other things, yes? Pies of various kinds, ice creams, candies, no? Dr. Majerick brought some kind of toffee yesterday. And he left it on the break table, and I tried it. Maybe it's a California thing. I don't know. It was different. I made it halfway through, and then I had to stop. I was like, I don't know. I shouldn't complain about free food. I'm not complaining. It was different. It was just not for me. Something about the juxtaposition of like rubbery candy and almonds just didn't set with me. I don't know. Okay, so we have function of x, right? On the other side, we've got a function of what? Of y. The only thing that's commonly a function of x and a function of y at the same time is an ordinary garden variety constant, right? So for reasons of linking with my initial 4 propositions, I suggest we set this equal to minus k, right? If I do that, then that gives me x prime prime plus kx equals to 0, and y prime prime minus ky equals to 0. So I've, by separation of variables, I've replaced, the Laplace equation is essentially been replaced with the corresponding problem of solving these, at some level. Now, the reason I wanted to make it look like x prime prime plus kx is because the boundary conditions that I've been given for x are kind of like the most nice, right? So these are the ones I want. The boundaries, the y ones are a little bit funny, but the x boundary conditions are most like what we've done before. So this says my intuition is to start here and try to build my formal solution from this thing. So that's why I put the k to make it look like on the x, because then I can link up with my previous, like, proposition 2 or whatever. Okay, so let's convert the boundary conditions. So what is the boundary conditions? So this step 1. Step 2 would be to recognize impact of boundary conditions on the spatial solution x. So in particular, we have partial u, partial x at what? Partial u, partial x at 0y, right? Which would be x prime of 0 times y of y. And partial u, partial x at pi y would be x prime of pi times y of y, right? Now these are equal to 0 for all y, right? So that implies that we must actually have x prime of 0 being 0 and x prime of pi being 0, because otherwise we'd just be looking at the 0 solution alone. So we get, here's the corresponding boundary conditions for x, which is great because that takes us back to our initial the initial problem that I posed, which was solving the boundary value problem, right? What did we learn? This. So let's put it all together. What are we're facing a boundary value problem, right? We need to solve x prime prime plus kx with what? X prime of 0 equals to 0, x prime of pi equals to 0. We did this before, and we figured out that k has to be what? As I recall, k equals n squared. Well, what was it more properly? It was, how did it go? N squared pi squared over L squared? Right? I know it's been a little while since we did this, but isn't that right? N squared pi squared over L squared. That's my, you guys are hanging me out to dry here. It's not really saying, is it? So you guys are not excited about the FLOTUS? Woohoo. You're not going? I will give bonus points for math-related heckles. Sure. If you can get a quality heckle into that convocation, and it can be witnessed by at least one of your peers, preferably with cell phone footage, I will consider bonus points. That's exactly where it would go. Well, I think for that to happen, I would first have to invest more time in the proper formulation of math pranks. I need to have a set of about like 30 high-quality viral math pranks that I could kind of like get my viewership going on and develop a fan base, promote my channel, so forth. Yes, but I have not put the time into it. So
you should do that.
Should do
I'd
it.
like to see your math prank videos.
Yeah, you've got not like a victim of your math pranks, but I would love to witness others.
I feel like math pranks would all happen during residential math tests, though.
But if you just like,
Be like halfway through a test, and then I'd be like, get one of those like foghorns, like the, that judge on The Voice. He's got the foghorn. He goes, eh. No, not The Voice. The other one that's ripping off The Voice. The one with the Puff Daddy or P Diddy. What's he called? I forget. I don't know. Sean Combs, is that it? I don't know. What do we call him? That guy. But his collaborator, who, what is it? He's a DJ, right? Some kind of DJ guy. He's got the horn, the air horn. It's like I have one of those, right? Interrupt the test, like mid-test, and like put the air horn on, and then be like, problem number 3 is not really on your test. You've been math pranked or something like that,
I have a teacher in high school that would go around and take pictures of us when we were taking tests, and he had an entire Instagram account, and he would caption, like,
Oh, really?
those things that, like, I would say.
You would so get sued for that now.
Yeah. Private high school.
Private high school? I have thought about bringing my camera in and like turning it on the students during the test and posting that video for that day of the class.
See if you capture with some tears or something.
That does sound like a lot of fun.
Hilarious captions for a lot of us.
I could, but I feel like that's a pretty good way to get fired.
Make it a private account.
It would be admittedly a good way to get fired. I'm not just using that as a figure of speech. Like it would be,
You gotta get fired.
sorry we have to live in an apartment now, but it was a really good joke. Yeah. Anyway. People have got fired for jokes here before. It's happened. Maybe joke goes, see, if you tell a joke to a student, and the student tells their parents, and then parents don't understand it was joke, and then parents go to administration. Administration doesn't go, maybe I should talk to the student and find out if they're actually, like the professor and the student are friends. No. That's not how it goes. It just becomes a full-fledged investigation of professor, and then professor, oh well. Nice knowing you. So yes, math pranks. Hey, you guys distracted me. You're bad people. But yes, this is the characteristic value, n squared pi squared over L squared. We worked that out. It's proposition 8.3.2 on page 203 in my notes. And there we learned that that's what k has to be. And we also learned that you need cosines, right? Xn. It's written in terms of the names and characters have been changed to protect the identities of the math. But it's the same thing. Cosine of n pi x over L. Now what's L here, though? L equals to? What are we doing here? We're looking at the x solution, right? And the values for x are bounded between 0 and pi. So L is pi here, which is wonderful because that gives us k equals to n squared. And xn of x is just what? Cosine nx. Woohoo. Now, by the way, n could be 0, right? So we get not just one x solution, but in fact infinitely many. Yay, right? And then once you know that, you can go back and try to find, at the moment we've only solved what? We only really satisfied the partial u partial x and partial u partial x conditions at 0 and pi, right? We have not yet put into play these, I would call these initial conditions, although admittedly that's kind of a weird distinction to make. Why is time? What's the question?
How did you find that L is equal to pi?
Oh, this is, L equal to pi. It's because we're doing this for 0 less than or equal to x less than or equal to pi. So that's what we called L in the proposition. This is a very good question. You guys are, it's your class. Ask questions. Proposition 8.3.2 on page 203. And that's where we worked through those three cases, right? We looked at sine, cosine, cosh, sinh, and then the linear, and we ruled out two of the cases, and we just left with the one giving us interesting solutions. Okay, so then let's go back to the y. Y, we have what? We got y prime prime minus n squared y equal to 0. So therefore lambda squared is equal to n squared, which implies, of course, lambda is equal to plus or minus n. Anyway, long story short, we have y sub n is equal to something like, I don't know, an cosh ny plus bn sinh ny. Right? And what if n equals to 0? That would just be what? Something like a0 plus b0y, right? Because n equals 0 gives us y prime prime equal to 0. Integrate 2 times, we get a linear polynomial in y. So that's my x solution, that's my y solution, and we can put these together to make the product solution, right? So my formal Ooh, I think I can get away with erasing this now. I'm going to do that. So the formal template, as I call it, I think, we have u of xy equals to something like x0, y0 plus the sum n equals 1 to infinity of xn, yn. All right? Now, that is, so the x0 solution was just what? Oh, I don't think I really explained. I don't think n equals 0. What should I say x of 0 is? I mean, in principle, it would be some constant of x plus, some other constant, right? Just integrating x prime prime equal to 0 2 times, right? But then what are we told? We're told that we're also stuck with the boundary conditions, partial x prime of 0 and x prime of pi are 0, right? What is x prime, though, if x0 is c1x plus c2? X prime would be c1, right? So c1 has to be 0. So in other words, in the zeroth case, x sub 0 of x is just a constant c2. Okay, so in summary, we really just need a constant. This is x naught is a constant, so without loss of generality, we have a0 plus b0y plus the sum n equals 1 to infinity of what? X of n, which was cosine nx. I'll write the an first. An cosine of nx cosh of ny plus bn cosine of nx sinh ny. And that is going to turn out to have all the flexibility we need to fit the initial conditions. All right? So we'll use, in general, we'd use the Fourier technique here to fit the initial conditions. All right? I don't think we actually need to do any Fourier integration today because the initial conditions which are given are pretty nice, pretty simple. Let's start with the one at 0. U of x 0, what's that equal to? What? Better what?
Oh, I let him borrow a pen.
Oh, you shouldn't. You shouldn't let him borrow a pen. How's he ever going to learn his lesson if you do that?
Yeah, you won't learn your lesson.
Wait a minute. Who are we talking to? No, I do want Ian to take notes. You can give him a pen. I'll allow it. Let's see here. Good sneeze. All right, let's see here. It seemed appropriate. Where are we? I don't think I need to edit that out. I think I've been sufficiently vague. I don't need to edit anything out today. Let's see here. A naught plus B naught y. Goodness gracious, where was I? Oh, yes. Okay, so plug in y equals to 0. What do we get? We just get a sub 0. And what happens when you put y equals to 0? Sinh of 0 is what? Just 0, right? What's cosh of 0? It's 1. So this whole sum becomes the sum, n equals 1 to infinity of a sub n cosine of nx, right? So all I'm doing at the moment is just plugging that boundary condition. I'm calling it an initial condition. Admittedly, that's, I don't know, I mean, the other boundary condition is probably a better thing to say, the x boundary condition. Or is it the x boundary condition? I mean, it's really the y boundary condition, right? This is, the top one is for y equals to 0, right? And the bottom one is really happening when y is equal to 1. So in some sense, these are the y boundary conditions that we're working with right now, right? That's probably a better thing to call them. Let's say we're working with the y boundary conditions. So the y boundary condition at 0, when I put it into the formal template solution, gives me just a constant plus the cosine series. But that has to match what? That has to match the given y equals 0 boundary condition, which is 4 times cosine 6x, right? Plus cosine 7x. So you guys tell me. We don't need the Fourier technique, right? The reason for that is that the given boundary condition at y equals 0 is already a Fourier polynomial, right? It's already just a sum of cosines. So you can just straight up read off from this by inspection what? By inspection, I can tell you that a sub 6 is equal to 4, and a sub 7 is equal to 1, and a sub n is equal to 0 for n not equal to 6 or 7. That's it. Does that make sense? Yeah. Questions? Yeah. Y sub 0. Oh, y sub 0. That's because n sub 0, n equals to 0 gives me y prime prime equals to 0. So if I integrate that with respect to y 2 times, I just get a linear polynomial in y. And that's it. I mean, there's no, hey, y of 0 is 0 and y of 1 is 0 or something like that, right? The y boundary conditions are more nuanced. They don't allow us to just well, in fact, you could figure out that a sub 0 has to be 0 if you looked at the boundary condition u of x comma 0 being that. Well, that's what I'm doing here. I don't know if that answers your question or not. Sure. I mean, y prime prime is meaning second derivative of y with respect to y, right?
Yeah, I'm just
Okay.
not really sure why you don't just plug it into y. Why you don't just put 0 into that.
Oh, because the b not y term.
Yeah, I just don't understand why it was like.
Well, there's no b not y term in this.
Right.
If I put n equals to 0, I just get a sub n. The sinh is 0, so that's not even present. What I'm saying is it's really a separate thing to have that there. Yeah? No? Was there a question?
I have a question about the equation.
Which one?
Step 5. So the a naught plus b naught y equation. Should on the far right, should that be bn sine nx sinh ny, or just cosine nx sinh ny?
Well, when I'm the xn is literally cosine of nx, yeah, and this is an cosh ny plus bn sinh ny. So what I did was I just
Okay.
multiplied through to get that, and just put the constants out in the front. I don't know if I must not be hearing you, Taylor, because you know how to integrate y prime prime equal to 0, and I'm not hearing your question somehow.
I just was looking at the wrong.
Oh, okay, okay. So no.
It just doesn't make sense why they don't give the same answer, but it's okay. I see
Oh,
what you're doing.
the difference is that in the x case, we have the boundary condition that x prime of 0 is 0. X prime of 0 is C1 is 0. So that's why I just get the C2 in the x case. In the y case, I don't have y boundary conditions that are like y prime of 0 and y prime of 1 or 0. I mean, the y boundary conditions are these things, which are, I mean, I could look at y of 1, and I do think that that has to be 0. And maybe that's reason enough, because y of 1 would be what? So y sub naught. But again, well, anyway, I'm going to go on, so I don't think I'm helping. So the other boundary condition here at y equals to 1 is what? U of x1 is 0. So what's u of x comma 1 equal to? Well, apparently, we just learned what? That, well, let me just work it out here. So u of x1 is a sub 0, which we don't even need to write anymore, right? And b sub 0, which, well, b sub 0 might be non-zero, we don't know yet. B sub 0 times 1, right? Plus the sum of, and I'm just going to leave it symbolic for the moment. I mean, we already know that most of the a sub n's are 0. All right, but let me just leave a sub n not explicitly using these just yet. It'll be more convenient to use them in a minute. So we've got cosh of n plus bn sinh of n, because y is equal to 1 here. So we've got that. Right? And that's equal to what? It's equal to 0. Oh, did I lose my? Oh yeah, thank you. That actually, I was about to get really confused, so thank you. So equating coefficients again, now we learn that b sub 0 is equal to 0 because there's no constant on the other side, and also an cosh n plus bn sinh n is equal to 0. Hey, that's nice. That says that bn is equal to what? minus an cosh n over sinh n for n equals to 1, 2, and so forth. That's pretty nice because that means that b sub n is also 0 for n not equal to 6 or 7, right? And only n equals to 6 or 7 gives me non-trivial b. So now I can write down the solution. I've figured out what my constants have to be in the formal template, and that's it. So let me write it out. I'll write it over. I'm going to erase these at great stupidity. But so what we have then is u of xy. Let's see here. I'll start with my n equals to 6, which has got what in it for me? We've got a cosine of a sub. What is a sub 6? So 4 cosine of 6x, right, times the hyperbolic cosine cosh of 6y, right? And then what's my, then my b6 is what? Minus 4, right? And how's it go? Minus 4 cosh 6 divided by sinh 6 times the cosine of 6x times the sinh of 6y. Right? This is all the n equals 6 term. And then the n equals 7 term is just cosine of 7x cosh 7x, yeah? 7y rather. And then minus hyperbolic cosine of 7 divided by hyperbolic sine of 7 times the cosine of 7x times the sinh of 7y. That's my n equals to 7 term, yeah? And that solves the boundary conditions I just erased in the Laplace equation. So this is actually problem number 1 from section 10.7, I think. And you know, when I first worked this out, so I taught this course at NC State before I taught it here, and it just happens that the organization of the course is a little bit different. And at NC State we have a whole course. They have a whole course in PDEs, which comes after this course, and so I never really worked out this stuff in this book at NC State, even though we use the same book at NC State for differential equations when I was there, when I was teaching. And so one of the, you know, I think it was, I don't know, so I could summarize here or something. I was working through these problems, you know, working them out, and I worked this problem, and I got the answer, and I think I got this answer, you know, and I was like, yay! And then I look at the answer in the back of the book, and it just looked like an entirely different thing. I'm like, what's going on? And so the thing is, this can be simplified in a rather interesting fashion. Let me see if I've got it in my solution here. See, because there's like adding angles formulas for, so this is the problem we've been working on. And you see, at this point in my, what's all this? What's all this? What's all this stuff here? This is me working through proposition 8.3.2 in the context of this problem. At some point, I got tired of doing it in all the problems, and I relegated it to 4 propositions. So anyway, after the dust settles, we get to the formal template solution, which I've called star star, and fit my boundary conditions at y in, as we just did. And lo and behold, I get to the And that's, I've written it in a different way though, haven't I? What did I do? Cosh, great. We got those terms, you see them, right? Let me underline them in green over here. So you can easily see these terms sticking out at the front, right? Those ones. And then these two are just a kind of funny way of writing these guys, right? So what did I do? I did like cosh of 6 over sinh of 6 is what? It's 1 over sinh over cosh, right? Which is 1 over the tanh. So that's where that's coming from. Yeah? And then I collected the cosine 6 terms and the cosine 7 terms together, and it gives you these. And then what I do? I made a common denominator. I pulled my sinh 6 out, sinh 7 out, and give me this. And then there's an adding angles formula for cosh and sinh, which allows you to rewrite the answer like so. And that's the answer that's in the back of the book. And that answer actually is to be preferred because it's manifest that that solution satisfies the boundary conditions that were given. You can easily see from this, especially, it's even better if you factor the 6 out and get like 6 times y minus 1. If you put 6 times y minus 1, you put y equals to 1, what happens? You get sinh of 0, which is 0, right? Put, again, factor the 7 out. When you plug in 1, you can easily see that we get 0 because we get a sinh of 0 here and here when we put y equals to 1. On the other hand, if I put y equals to, oh man, I've erased it. I wrote them up here. And at the other hand, if we put y equals to 0, what happens with these? We get sinh of minus 6, right? So that sinh of minus 6 cancels with the minus sinh 6 out here and just leaves you the 4 cosine 6x. And on the other hand here, when we put y equals to 0, we get sinh of minus 7, which cancels this minus sinh of 7 and leaves me the cosine 7x, which is exactly the voltage function that was given on the lower boundary of the rectangle. So you can see that the answer checks even. It's harder to see that the answer checks if you're using this formula. You could still do it though. Anyway, whatever. So that's Laplace's equation. Obviously, we could have done what? What would have made this problem substantially harder from a calculational standpoint is if instead of giving you a Fourier initial boundary condition down here, which is already sums of cosines, if we'd done something that was actually requiring the integration to calculate the Fourier coefficients, right? So I think the problem as it stands is not insane for the final, but it's still probably a little bit much. I'm probably not going to ask the full problem like that on the final because you guys got so much else going on, and heaven knows you need to study eigenvectors. So, well, I know that you need to study eigenvectors. I'm quite certain of it. All right, so let's see here. Let's talk about variational calculus for the remaining time. So what is variational calculus? Well, it's an old part of calculus that is just kind of drifted out of the mainstream for the last, I don't know, 100 years or so, as we discovered more rigorous things in the 19th century, like work of Cauchy and Weierstrass, those kind of people. We've learned more and more sort of ways to be careful about calculus, right? So as that happened, the calculus sequence became more logical, but it also lost some of its adventurous initial spirit, which was contained in variational calculus. So to maintain the same level of rigor that we give you guys in calculus for variational calculus, it requires a lot more background. And so that's part of the reason that it's been dropped from the predominant undergraduate curriculums that you'll find out there. I mean, it's not often taught. It's often you'll find this as a graduate course, but doubtless that has been annoying to physics departments because variational calculus is important and really foundational for the way we look at modern classical mechanics. It's all written in terms of variational calculus. In fact, variational calculus is a common theme, a thread which is woven throughout the equations that guide modern physics. Almost all of them are written in terms of some action principle. But here's some questions that variational calculus seeks to answer, like what's the shortest path between 2 points on a surface? What's the path of least time for a mass sliding without friction down some path between 2 given points? What's the path which minimizes energy for some physical system? Given 2 points on the x-axis in a particular area, what curve has the longest perimeter and bounds that area between these points in the x-axis? If you look at all of these questions, what are you searching for? What's the variable that you're varying? You're looking for a path, right? I mean, it's a whole function that's the variable, is the viewpoint. So that's why it's different than in calculus. We don't typically vary a whole function. We'll vary a particular parameter, right, that traces over some class of functions or something. But we won't actually thinking about taking the function itself as a variable, and that's what variational calculus does. So let me just get to it. Here's the variational problem, the standard one. Look at something like the Lagrangian. The Lagrangian would be an integral of some function of y and y prime and x, integrated from x1 to x2. And I study in these notes here the condition that so what I'm looking at is a family of functions y of x comma alpha such that we vary the function by this little variation eta of x. And as alpha, and the eta of x is chosen so that it's 0 at the endpoints. So a picture that's probably should be drawn here is something like this would be perhaps x1, x2, and this is y of x comma 0. And then eta, it gives you this little, add eta to it in such a way that this might be y of x comma 1, which is y of x 0 plus 1 times eta of x, yeah? So now if you did alpha equals to minus 1, it would be what? It would be like the same thing, but down here, right? I don't know if I can do it. And then as alpha varies, you're swinging through this whole class of functions that are related to the center function, which I drew in black. So given a function, we can talk about the variation of the function by adding this little eta, which goes to 0 at the endpoints. And so we define the variation of y to be this delta y. It's equal to alpha eta of x. This is the variation in the proposed solution. All right. And so then, if you look at the functional, which is in this case the Lagrangian, if we look at the Lagrangian as a function of alpha, right, for a given eta, then we have a function. We have f of y of x alpha, y of x alpha prime, and x. So we can also look at this as a problem in multivariate calculus, really. And so the principle of least action says that you want to minimize that Lagrangian. So we want to have that partial j partial alpha. When we plug in alpha equals to 0, we want that to be 0. In other words, we're trying to set up conditions which make that y of x 0 to be the specific function which makes the Lagrangian maximized, or minimized perhaps, right? Anyway, a critical function. We're looking for that critical function which makes the Lagrangian biggest or smallest. In fact, we're looking for smallest. We're trying to minimize the Lagrangian. But the argument is that if you look at this family of paths which are related to the optimal path you're looking for, that should correspond to the problem of just differentiating with respect to the alpha, which is corresponding to the variation, and setting that looking for the critical point with respect to alpha for a given eta. Now that's just calculus 3, more or less. And so you differentiate, swap the order of integration and differentiation. This is the plain old garden variety chain rule. We have to partial differentiate f with respect to its inputs, which are y and y prime. Here, y and y prime are be taken to be independent variables, right? Which I suppose technically means you're working on a jet space or something. But anyway, so you have that. But then there is no x dependence on alpha, right? Alpha has nothing to do with x in this setup. So that's 0. And y prime, partial alpha, you can see from the formula, which I should write here. I mean, it's right here. Y of x comma alpha is y of x0 plus alpha eta of x. So if you, in y prime of x alpha would be what? Y prime of x0 plus alpha eta prime of x. That prime is an x derivative. And so for that reason, partial y prime partial alpha is just eta prime. And partial y partial alpha, well, that's just straight up eta. And then we've got this. Then we integrate by parts. And so integrating by parts allows me to trade this d eta dx instead for a total derivative of this product and the derivative with respect to x of partial f partial y prime, like that. And so that gives us partial j partial alpha is this, but one of these terms is a total derivative, so we integral the total derivative just gives me the quantity evaluated at the endpoints, and then I've got this. Now, assuming that we're looking for a function which vanishes on the endpoints, that term goes away, all right? The initial term goes away. Then we need to make this somehow be 0, right? But this has to be 0 for any choice. Like the setup has to work for all possible variations, all possible etas, right? So it stands to reason, since the initial f is given, that characterizes the Lagrangian. I mean, I think the f actually is the Lagrangian. The integral of the Lagrangian is actually the action. So we're minimizing the action to be more precise here. But since this holds for arbitrary eta for a given f, the only way that can happen is if this quantity is 0. That makes sense? I mean, that makes sense. And this being 0, that is exactly what are called the Euler-Lagrange equations. So that is a quick derivation of the Euler-Lagrange equations. And I have confessions here about why I'm cheating as I tell you this, but there they are. Euler-Lagrange equations for f, just partial f partial y minus d dx of partial f partial y prime equal to 0. These are the Euler-Lagrange equations, which will minimize this action here. So the reason they're called Euler-Lagrange equations is Euler did it first. Euler's, the famed 18th century mathematician. Lagrange is the end of the 18th century, right? The way Euler did it was to think about the path he was looking for. He did something like say, well, the answer I'm looking for, I can think about this path. I can think about there being points on the path, right? And if I think about there being like a bunch of points, I can give coordinates to each one of those points and then come up with a system of maximizing equations for each one of those points and put it all together, and that should find me, the optimal path. And then somehow from all that, he extrapolated the Euler-Lagrange equation. I don't know. I've never seen it. I've just heard people describe this calculation. To me, that is monstrous. What Lagrange did, on the other hand, is more like section 13.3, and that method of viewing variational calculus is still practiced in the physics community to this day. It looks like this, which is you just take a variational derivative, as it's called. And so in some sense, this is just formal nonsense. you just take delta of it. And so delta is a derivative. You can commute it with the integral, and then the delta's got a chain rule. And and you can commute delta and d. Of course, like why not? You can commute the delta and the d. There you do. Just do it. And yeah. And so we get to the same thing. And then since this holds for all delta y, we get that the Euler Lagrange equations are true. This is how it was taught to me in my junior level physics course. And so when I asked a question like why does delta and d commute, they were not able to give me a satisfactory answer because it's formal nonsense. And I'm asking exactly the question which this method does not explain. So my previous section is really at least a first attempt at formalizing the variational derivative. But that's more or less how Lagrange thought about it, like this. And an important thing to remember about physics is physics, as it relates to mathematics, is a sort of time capsule. Whenever a particular part of physics came into being, it tends to like freeze in time that part of mathematics, and it just keeps it. It's not common in the physics community to actually update their equations to be mirroring current mathematics. So you'll find some 19th century mathematical ideas in physics if you study it, because it's just, as a point of culture, maintained there. You can restate the Euler Lagrange equations like that. I really want to get to an example for you guys. Here's a nice one. Let's find the shortest distance between 2 points in the plane. So in this case, the Lagrangian that we're going to look at is the square root of 1 plus y prime squared, because this is the arc length integral, right? So the question is which choice of y will minimize the distance between two given points in the plane, right? And so in this case, partial f partial, this is my f, right? Partial f partial y is 0, partial f partial y prime works out to that. And then the Euler Lagrange equations lead us to ddx of partial f partial y prime is this. And so if that's equal to 0, that means that this is equal to a constant, right? And if that's equal to a constant, well, you can square both sides, and then you get this, which then gives you that dy dx is plus or minus the square root of that. Call it m, integrate, you got a line. The shortest distance between 2 points in the plane is a line. This is how variational calculus derives that. I will not talk about that one. This one's interesting, but I should probably not talk about this right now. But I will. Just briefly. The Berg-Christochrone problem asks the question, if your particle slides freely along some curve from x1, y1 to x2, y2 under the influence of gravity, what's the curve of quickest descent? So what you're trying to do is to minimize time for the bead sliding down some wire without friction, right? The question is what shape of wire gives you the fastest descent? And we're assuming, of course, that x1 is not equal to x2, because if x1 is equal to x2, everyone knows the answer, right? So, oops. Anyway, this is time. This integral represents time, because v is what? What's v? It's ds dt, right? So dt is ds over v, right? And so what this is ds over v. But I'm also assuming that it's without friction, so I'm using conservation of energy to write the v. But the top, so this is exactly ds, and this is v, assuming conservation of energy. Now, this problem was studied by all of the most prominent physicists of their time. I mean, I think Newton studied this problem. The Bernoullis studied this problem. I think Galileo studied this problem. Then Galileo came to the conclusion that it should be a parabola because he didn't have the correct mathematics to work on it.